So,
Okay.
I'll just introduce. So Nikos is here tonight. I'll tell him when his slides have uploaded, and he's going to give his personal introduction right now. So thanks for all being here, and enjoy the evening.
Hello, everybody. My name is Nikolaos Dilegiannis. I am professor of machine learning and AI at the university here at the University of Brussels. I have a group of several researchers affiliated also with IMEC, the Institute of Microelectronics in Belgium. And we are focusing on, I hope this is working properly, all right? So we are doing research on different aspects of artificial intelligence and machine learning with focus on explainable AI, distributed AI, distributed deep learning, with various applications. The applications in my group are typically focusing on social media analytics, so big data in general, but specifically social media analytics, recommender systems. So basically, how do you design efficient algorithms that run on the cloud and they provide recommendations to users? For instance, personalized recommendations, context adaptive recommendations, as well as recommendations that they learn to adapt across time. But furthermore, we're working on applications related to smart cities. We will see some of these examples later on. And finally, applications that have to do with image and video mining. Okay? So do you have already any experience about any of these topics, or have you heard anything about these topics? Please.
Not in a practical way, just myself. I know about it, all of it, but I've never done it.
And someone else? No, but still excited to learn about these topics, I guess?
Yes.
Sure. So what is the your field of expertise? Can you say a little bit more about the generic things about yourself? Are you I don't think you're a data scientist, right? You want to be data scientist.
I am.
You are a data scientist. Focusing on?
Civil engineering application.
Yeah.
They're building.
Okay.
I'm working in a company here, providing services in civil engineering.
Great. In the meanwhile, I'm going to check how my slides are being.
You're downloading.
I'm
So I
downloading.
started the download here of the right one. So it's, I don't know how big it is, the file.
We're almost
Almost there.
Yep. Well, sorry for that delay, but I was trying to connect with my laptop there so that I can show you some cool demos and videos. I hope that we will be able to still see some of them while we go with my presentation, right? So any other experience in data science in general? So why are you here? What would you be interested in? Why would you be interested to know how to do? Please.
Me personally, I'm working in web analytics.
Okay.
A lot of web analytics people are doing data science. I might go that way, but before that I have to learn and see if that's the way I want to do.
Okay. Any other example? So today we're going to talk about diverse types of data, right? Structure, instructions, and so on and so forth. What is your view? Data that you collect from the web, are they structured or unstructured?
They are structured, all of them.
They have structure?
Yeah.
Such as?
Well, they are all kind of dimension data points, and they are, most of them, we always try to link them to a unique ID or visitor.
Mm-hmm.
So, from what I understood, is the definition of being structured.
Yeah.
They all kind of linked together.
Well, we'll see today some of these examples, right?
How large is your presentation?
It should be there.
We're at 52 megabytes. It's big data, right?
Yeah.
We don't do small presentations. You know the size of it, or
I don't recall the size of it, but
you look at it, it's your file. If you can see it quickly there, how much you uploaded. I don't know how much we have to wait for now.
oh, It's 300 megabyte apparently.
300 megabytes. So nice. The progress of the download is 50. Yes,
That's why it's taking so long. I'm truly sorry. I just tried to put it as interactive as possible with many examples. I was hoping that my computer will be able to connect and work properly like the previous time, but apparently it's not.
You have a new setup.
You have a new setup.
So it makes it more complex, but I would say just start explaining what's in there.
Yeah. All right. So, so you might have heard about the value of data, right? I will start by saying that there are different types of characteristics in big data nowadays, and all of them are well, we can, let's say, put them together into the form of 5 V's. And these 5 V's are, first of all, volume. Volume means that the data nowadays is extremely large, like my presentation. Secondly, we have the second V, which is veracity. Veracity means that the data is actually not clean, not perfect. They are corrupted, they are incomplete, they might be noisy, and some of them, they might be intensively changed so that they can lead to different results, all right? Then the other V is variety. For a given problem, we might have completely different types of data, all right? We have collect for a given problem, we might have collected diverse aspects of data. Think, for instance, of a street network, right? A street in your neighborhood. You might have collect data that have to do with the temperature in there, the pollution, the number of cars that they're passing, the speed of the cars that they're passing. All of these have different forms. There are different types of data. You might have collected even images of your street or videos of your street. So we have exactly the same source, which is the same, let's say, phenomenon, the observation of your street, but we are observing it with different types of sensors. And this leads to variety in data, right? Then the other thing, the other V is velocity. Velocity means that data change dramatically. Nowadays, I mean, I hope you are not so much irritated by the number of emails that you are receiving, but you must have observed that the number of information that is exchanged, in the number of, for instance, tweets, in the number of videos uploaded on YouTube, in the number of content shared on Facebook is vastly increasing, and it's changing with high speed, right? And then there is a fifth V. Can you imagine of the fifth V, the fifth word that describes the last component? Sorry? Exactly, value. Value refers to how can we use this data to extract important insights. How can we use this data to improve our business? How can we use this data to improve our lives? That's the fifth V that refers to the 5 V's of data, right? I think I will need my slides to go to the next quantitative aspects. Do you have the code for it? It's here. Oh, we are still downloading.
As we said before, 80% of any big data project is cleaning the data, waiting for the data.
Well,
this is a very painful reminder that when you work with big data, it's bad.
There's no way to that we can connect with my computer to make it faster? No.
We tried before to connect it.
Yeah. So, yes. Sorry?
Do you want a pen drive?
I can.
Do you want a pen drive?
Oh, USB. We tried that as well, but apparently the ones that are here do not.
There's 300, right?
Yes, we are almost there.
Another 100, right?
Another 100 megabytes, so by adding a LAN cable it might speed up.
I've never seen a presentation.
The network. Is there one we could use for that? Maybe in the meantime, tell us about the biggest data set you've worked on so far, size-wise, now that we're talking...
Well, there are diverse types of data that we have worked on. One of them is high-dimensional video, right? So I will give you an example of video data. We'll do the calculation together. But imagine how video is produced, right? So if we want to make an example of video, let's suppose that we have 1 megapixel image, right? 1 megapixel means that this image is constructed by 1 million pixels, right? 1 million pixels means that each image consists of 1 million elements. Each of these elements has 3 numbers, right? 3 numbers correspond to the three different colors: red, green, and blue. So each frame, each picture that you take, has 1 million numbers. 3 million numbers for each pixel. 3 million numbers, and each of these 3 million numbers has each of these pixels has 8 bits, right? So 24 bits. 24 bits, 8 times 3, times 1 million. So one image has 24 million bits, right? One image, compressed, correct? And now high-dimensional video typically is it takes pixels like 30 frames per second, or 60 or frames per second, which means 60 images or 30 images for every second. Now imagine that you have 1 hour video, you can do the calculations, and you can imagine what is the size of the information, right, that we're having. I will give you an example in my presentations that for a 5 minutes video, it was like uncompressed, it's something like 10 gigabytes, right? The same video that is in these slides, which are going to be soon projected, right? And hopefully these links work. So that's another aspect. That's one data set, and actually that's one unstructured, an example of unstructured data, video. The same thing is text. Have you seen? Well, text is another type of. Is it downloaded? Well, finally.
We have a presentation.
Great. Well,
You put it to the full screen mode, which is the icon here.
so why don't you click in there? Can you put it on?
Yeah, but that's on. We're looking for the presentation icon. If somebody sees it in LibreOffice,
Well, we
let
can
me
go
know.
to View, and then
Somebody in the room sees it, let us know. As you can see, we're all used to seeing the icon at the bottom. Ah, here, it is here.
Slideshow to the there, on top, slideshow to the right,
all right.
Yeah, it's in the top bottom here, that one, slideshow. No, higher,
Oh,
yeah.
sorry.
Yeah.
Oh, voila. Okay, great.
What a build-up, huh? You can feel the tension in the room.
All right, so finally we have my presentation here. This is the title of the presentation: Big Data, Types of Data, Real-World Samples and Opportunities. My name, that's it. Funny thing about my name is that I have the same name as Suze. Suze, you know Nike? It's exactly the same name. What is the male version of Nike? And you can see here my affiliation and my primary occupation. So feel free, here you see my contact details as well as my Twitter account. So feel free to follow me on Twitter or send me an email if you really need to talk to me. I would be really happy to answer to your questions. So as I said, we are living in the data deluge. Every day we are experiencing diverse types of data from different modalities. That refers to different video footage, different data from our mobile phones. Actually, we have to start thinking about why Google and Facebook and all these big companies, they are offering us services for free. What do they take in return? The answer is data. Data is currently in the markets nowadays a very valuable token. We are talking about a significant boost in the economy that is produced by data. Okay? Data is a significant token in the modern economy. But data is also produced by medical devices. When you go in the hospital and you have an MRI, this is basically a source of data. Data is produced by expensive experiments that have to do with physics, or that have to do with biology. For instance, the decoding of the human genome. Data is also produced by IoT, by the Internet of Things, for instance, this. And of course, we are producing data every time we are doing a search on Google or on other searching engines. We already described the 5 V's of data, right? And I would like to put particular emphasis on value. We will see today how we can extract value from data. And what I would also like to show you is some examples of data, of the volume of data, actually. We already claimed and we already described what is the volume, the variety, and the velocity. But here you can see, actually this slide is taken is made some years ago, and you can see already that the size of data in the different areas in the world is extremely large data sets, all right? We are talking about petabytes of data. It's important also to mention that data is produced by different sources. In the past, we had data produced by people to machines. That was the most old, I would say, example, right? As old as data produced in banks. So when you were going to a bank and you wanted to open a bank account, you would give your name, your address, and so on and so forth, and then someone would put this data into a database. This is people putting data into machines, right? So then we had people to people, which means that through social media, through web, we were creating content, right? And we were sharing content. But now, data is produced by machine-to-machine communications. I don't know if you have heard about the vision of the Internet of Things. Basically, things, sensors, devices, all connected to the web. And we are talking about an expectation for the forthcoming years of 50 billion devices connected on the internet, all right? 50 billion physical things, from a sensor to a pen, a fridge, a toilet, smart toilet that can measure the substance of your urine. All of this can be connected to the web, and you can see that online. Smart pills that you swallow, and then they take data, they create data from your whatever they are monitoring, and they are transmitting or processing this data. For example, when I was doing my PhD, I was working with smart pills that you swallow, and they take video of your gastrointestinal tract. So no need anymore for endoscopy, colonoscopy, and so on and so forth. And these systems are now produced, and they are available in hospitals. Okay? So in this slide, you will see the value, the expected value in billions of dollars Actually, these numbers have been already revised. For those that they are interested, I can give you reports about the expected value in the forthcoming years. These are already obsolete numbers that were created a few years ago. Now these numbers, I would say that they might have been even multiplied by an order of magnitude. And what is very interesting is that because data has become such an important token for the modern economy, there has been a significant change in the market, in the job market even. You can see that there is a trend that started from 2013, 2014, and this trend shows that one of the most prolific and the most important job descriptions in the future is a data scientist. And what is also interesting is not only data scientists are important, not only people that they understand data and they can manipulate data are important, but also people that they can create business opportunities with data. So data-driven business analysts and business developers will be also in great need and in great shortage in the forthcoming years. So going further in my presentation, I would like to speak about different types of data and specifically to focus on static and real-time data. So what is static data? First of all, with static data, we refer to data that they have a given form, a given size, and this data do not change their size and their form across time, right? Think, for instance, of medical images or even images, okay? They have a structure. It is in the rectangular form. Each one of them has a number of pixels. Each pixel corresponds to a number of channels, red, green, and blue, and each one of them is captured by a number of bits, for instance, 8 bits or 16 bits or whatever. So this is a structure, all right? This structure is kept. Other types of data that they are structured is open data. Open data, they follow specific structures. For instance, where are the hospitals? When I refer to open data, I mean that locations of hospitals in Brussels. Well, we don't have new hospitals every second, right? Yes, okay, we might have a new hospital after a number of years, but you can imagine that, you know, this kind of data have a given structure. The same thing for road networks, for maps. They are structured data, okay? So what is if I try to make it very, very simple, a structured data type is basically following a structured, a static data structure. And a static data structure is, for instance, an array of numbers. When we create an array of numbers, we give it size, and we say this array is basically corresponds to this, holds this data. Another example of static data is the Oecd data of Belgium or of a country. So these are data about the population, data about the education, data about the GDP, the tax, income, the emissions, and so on and so forth. They have a specific structure, a specific form, and these are stored somewhere with a given form. And let me show you how a static data structure has a form of a static data structure. So for road networks, you see an example in a GPX format. You see here that you have a certain type of information, and also this link is also connected to certain metadata. Also, you have here a text that characterizes Geraint connects, for example, and so on and so forth. You might have GPS data, etc. So this gives you an example of static data that they don't change across time. Other types of data that do not change across time is space data. If you go, for example, in the NASA portal, you can find maps of stars, right? And you can download this data, and this data is static. They don't change across time, of course, unless we find a new star, right? But there are also other types of data. For example, mobility data, smart city data, fintech data, or social media data that they really change across time. To give you an example, you can use apps like, for instance, Drive Now, and then the data in these apps change across time. What kind of data do you think that these apps collect or project? Yes? Sure.
About the traffic or about the pollution?
Well, first of all, this map, I don't have you, for instance, there are car sharing apps, right? Car sharing apps, first of all, they have data, they visualize data to you, namely the location of the cars and where they are in the city of Brussels, for instance, okay? These data, these are, for instance, every car is characterized, its location is characterized by a two-dimensional array, and this is the GPS, the longitude, the latitude of the car's position. But this changes across time, correct? So what other types of data do you think that these apps play with?
Availability of the car?
Yes? Sorry?
Movement?
They collect a movement, but what movement? First, they collect the movement of the car, but also they collect your position. Right? You are running it on your mobile phone. They have access to all the sensors of your mobile phone. They have access to your gyroscope, so they know whether you are actually sitting in the car or you're walking towards the car. Of course, they use that using the GPS. But they also have access to your proximity with respect to a car, right? Strictly speaking, they could know where their users live, because if I am a user and I always initiate, most of my times they go to look for a car for a given, I enter the app from a given location, they can really cross-correlate that with my schedule, and they could understand where my office is, where I'm living, where I spend my night. If I spend my night in a place where I typically do not live, right? So all this kind of data can be collected. But also they can collect information about whatever sensors they are available on your phone, so that we become a little bit aware of what data is about. Yes, please.
When you mentioned the route map, all those sorts of data,
Yeah.
movement may change according to the traffic.
The road network does not change based on the traffic. When I'm talking about static data and I'm giving the example of the road network, I'm not referring to the number of cars on the road, but rather where are the roads? Where are the buildings? Where are the roads? These typically do not change dramatically across time, right? I mean, we don't build new streets every now and then, right? No, I'm not referring to static data. Is the street information, is the map. It's not how cars move on the map. The location of a car, or the location of a human, of a user, is dynamic data. Okay? Well, the same thing for the Internet of Things. When you connect your car with a pollution sensor, you can, or your bike with a pollution sensor, you can monitor the pollution in the street that you are walking, right? And these data are dynamic because basically they change across time because they measure a specific phenomenon. And the same thing, of course, that comes without saying about fintech data. We know very well that the financial markets are very volatile and they change dramatically and very fast, and that's what people are trying to capture. And the same thing for social media. I mean, try to see how many tweets they are posted every minute. We're talking about millions of tweets, and you can imagine how fast how fast data change. So dynamic and real-time data have to do with, let's say, the velocity characteristic of data. Well, in order to represent this kind of data, we have specific data structures. And one of these data structure, for instance, is the linked list, okay, where you have a list of components. And basically what you have is that you have a head of the list, then you have a null element that terminates the list, and of course you have pointers from one element to the next element in the list. So this is an example of a linked list, a data structure that is used for dynamic data. This is an example of real-time or dynamic data. You have, for instance, an app of, if you use the STIB app on your mobile phone, right? If you use the metro, you will see that it shows what is the distance of the nearest vehicle, right? So all this information is in a JSON format. This you can see here a JSON format, JavaScript object identifier system. So it's a JSON API, application programming interface, which has this form of information, and you can you can consume this data actually yourself as a user. There are APIs available from STIB, and you can find what, for a given location, what is the closest means of transportation. You, for instance, you as a programmer, you have access to this information. The only thing that you need to know is how to understand and read from a JSON API and consume this data. Okay? Can you imagine what kind of scenarios you can build by knowing what is the closest tram to your location if you were a developer? I mean, of course, this is very important because it helps you to navigate in the city, right? But apart from an end user, if you were a business developer, could you think of business built on top of these models, business models built on top of these models?
If you're using an app for, I don't know, some kind of food or restaurant, and maybe the restaurant is closing, you could have some notification to tell you this restaurant is closing, but there's one open. If you take the photo, it's coming in 3 minutes, just beside you.
So these are exactly. So these are examples of context recommendations, and the context is the location, and you're recommending either a means of transportation or you're recommending a place where you can go and have a drink or have a bite. So these are this kind of systems, and actually the trend of recommendation engines, a trend of recommendation systems, is to go into this context adaptive and highly personalized recommendations. We will see in the forthcoming slides how you can, what do I mean by recommendation systems. So this is another example, again with a JSON API, of a real-time dataset. You know that with your smartwatches right now, you can basically monitor your heart rate. And these sensors, they are connected on the web. And based on JSON API, you can get your heart rate on your mobile phone. So that's the idea. Or even you could use this kind of sensor to monitor the heart rate condition of a baby. As a parent, you can use this device. You can put it on your baby, and you can basically use your mobile phone to see the heart rate of your baby. It might seem to you extreme, but there are babies, for example, that premature babies, that they are born with respiratory problems, because you know when a baby is born, the last thing that is produced is the respiratory system. And by using this kind of devices, you can really understand whether your baby is coughing, for instance, or whether it's breathing and everything is okay, right? So this can be used as an alarm systems, but also as systems that they can monitor your well-being, your stress. If you see the stress level to increase because of your heart rate, for example, these kind of apps, they provide recommendations to you to do something relaxing. Have you heard about this kind of applications? So these are examples of static data and how they are produced. Another example of such type of data is the Velo stations, where you can go online and you can immediately see what is the available Velo bicycles in each station. Again, here you see an example of the JSON API. I took a screenshot of the JSON code that you can go online and you can connect to it, and you can get information about the location and about the number of bicycles. Everyone that has a certain experience in the JSON format of data can do that. So you can go on the web and you can crawl all this information to know where the bikes or where there are available bikes. So you can use them when you develop apps, for instance, or you can use them as a kind of infusion model, data infusion in your business. Well, I still hope that that this works, but if it doesn't work, I will show you a demo of that later on. All right, so I'll try to show it. What kind of things can you do with this kind of data? First of all, it's interesting to do visualizations of data to see how data is changing across time and across space. What we have developed in my lab is a virtual reality data visualization tool that takes into account all these big data sources, including social media, including data from the positions of STIB buses, and also the availability of Velo stations. And everything is projected on a 3D environment. You wear virtual reality glasses, and then you're able to navigate in a virtual environment, and you're able to see what's going on at that time, at this specific moment in the city of Brussels, for instance. All right? You can click with your finger on a bus, and then you can see the location of the bus, where is it going, and so on and so forth. Our goal is to be able to make a big data visualization platform for authorities, for planning, for officials, such that we can understand events in the city, right? Let's try to see whether we are able to see the. Yes, please.
How do you recreate the environment? Is it based on pictures, or is it based on, like, what you see is what is happening right now in the place, or you can, let's say, get access to real-time data touching the element, but it's not
That's a very interesting question. And the answer is, I would say, is also linking what I just said before. So the visualization consists of different data. We produce a visualization by fusing different types of data. First of all, we use static data. Static data is that we have a library from a map company, a map creating company, and that is, for example, the company is called Mapbox. They create a virtual environment, right? And you have a virtual 3D map. Okay, that's a 3D map of the city. So that's a static data type. Is a road network, right? In a 3D format, not in a 2D format, but in a 3D format. And then on top of that, we fuse the data from all these APIs. We take real-time data from social media, from the STIB API, and from the Velo API, and then you're able to see what's going on in the city, a virtual representation of what's going on in the city by combining static and dynamic or real-time data. Does this make sense?
Yeah.
Okay, so here you can see, I hope, basically you see whatever you would see as a virtual reality user, right? So you see here the static environment. This is, all this map is a static data type that we load. Actually, whatever you see over there is also a static 3D environment created by these virtual reality software programs. You see here on the top some information, right? So you see the weather. We also take data from a meteorological API. You also see the air pollution in the entire city. And at the same time, you see here social media clusters. So basically, we geolocate what users are saying, and then you put these clusters on the location where they are. So for instance, if you have the possibility, and here you see the buses that they are running in the city, right? So here you see a bus that is in the park. I hope you see it here. There is a bus there running inside in the park. That is impossible. You never see a bus in a park, right? Do you know why is that? Can you imagine why? Sorry?
Under the park?
No. Well, it might be the case. Yes, you might be right. But here you see, the bus is basically going into the park. That's not the case. But what happens is that there are, of course, errors in the APIs, in the sensor measurements. There are problems with the GPS data when if, for example, the bus passes through a tunnel, or if the bus passes through a lot of trees, the signal to the GPS is getting lost, or if it's very cloudy, for example. So all these, they create errors in the data, and they have to do with the veracity in the data, right? Sometimes also the API of STIB, I don't know if you have worked with that, sometimes it freezes, and this is so is it this one? Yeah, exactly.
Why was it moving so much?
Sorry?
Why was
the moving.
so much?
Oh, sorry for that. But it was my my colleague who was moving with his fingers and with his face, right? So basically, the video is recording exactly what my colleague was seeing. So he was moving with his head because he was wearing the 3D virtual reality glasses. He was moving around to see this, to see that, and immediately you would see this flickering on the screen, which is annoying. I accept it, but at the same time, it shows you that this is a real system, that it works real time.
And is that data what you're using all publicly available?
Absolutely.
Yeah.
Absolutely. Well, if you're interested, you can send me an email, and we can invite you over to use it. Okay. Another thing that I wanted to show, another example of public data that is extremely interesting, is health data. So typically, this would be one line, and data should be on top, but it's fine. So there is a specific API, which is actually a part of Twitter. It's called Health Map. And what it does, we will use the link. What it does is that it visualizes real-time, well, let's say varying or dynamic data from epidemic reports. You know that when there is a very important health issue, hospitals or health organizations report it to the national health organizations and then to the international health organizations. All this data is collected by Health Map, and then they are pinpointed on a map which you have access to. We can now go and see. So this is, for instance, a flu and Ebola map. Oh, what do you think? Let's block it. So Belgium is here, right? And you can see, for example, the incidents in Belgium that have to do with epidemic issues. For example, you see that in May 14, 1 dead in Ghent. And then you see the information about it. So if you are, for instance, a health organization, then you're able to get access to this data and use this data from purposes that you might wish to have. For instance, cross-correlating this data with medical records, cross-correlating this data with social media, or companies do that with cross-correlating that kind of data with searches on the web to find for symptoms. Imagine you are Microsoft, you are Google. When people in a given location, they are searching something with symptoms, with keywords that are symptoms, you can immediately understand if these people are having a probability of suffering a specific disease and where they are. So they are able to monitor the outbreak of viruses using this kind of systems. Right? I mean, imagine, have you ever had fever or something like that, and then you type on Google fever or whatever? I mean, I have done it. I don't know about you. I have done it. So people do it, and based on that, these giants are able to monitor how, for example, diseases are spread, and what is the probability of this. Do you have any question about that? Does it sound fascinating? Whoop. So let's see now other types of data, structured and unstructured. Well, that's an easy one. Structured data have a given form. For example, phone addresses or product descriptions or IBAN bank codes, they have a given format, and this format is very easy to monitor. Okay, they have a specific type. They are structured. They have fields that they have data, and so on and so forth. But there are other types of data that they are unstructured, and these types of data is images and video. Social media is data that is completely unstructured. The same goes for text, for emails, but also for audio and sound. Let me give you a table which shows the characteristics between structured and unstructured data. So structured data, they have predefined models. Typically, they are text only, and they are easy to search. But unstructured data, they do not have a predefined data model, and can be anything from text, images, sound, video, or different other formats, and it's very difficult to search for it. So to give you an example, and we will see later on a solution to this example. Do you know Google Images? Do you think that this is structured or unstructured data? So an image is unstructured data, right? Especially video. But what happens if when we search in Google, we give a keyword and then you search for it? How do we search? How do we find images that they are similar to the keywords that we already gave? Yes.
Because not using like images, using the tag in image.
Exactly. Exactly. So there are images, they are tagged with metadata, right? And then you use the text to search within this metadata. Actually, you're not searching for a text that maps with the image, but you're searching with the text, a query that matches the text that characterizes the image, right? So you're not searching with the image. Could you consider searching with text? I mean, if you wouldn't have these tags, if you wouldn't have this metadata, then you would not be able to search an image, right? So we'll see later on examples of using artificial intelligence to search using text for images that they have absolutely no metadata. So basically how you can use text to explain what the image contains. All right? We'll see such an example. So a very important characteristic of structured data is that they reside in relational databases. Have you ever heard about relational databases? Yes? Great. And also in data warehouses. However, unstructured data, they either exist in blob storage on the web, or they live in NoSQL databases. Do you know what NoSQL means? Well, not only SQL, right? And typically, they generated both of them either by humans or machines. And here you see some typical examples of structured and unstructured data. So airline reservation systems, they are typically structured data. But however, word processing, text generation, this is unstructured data. Also, CRM systems, they are structured data, but emails of clients are completely unstructured data. And here you see other types of examples, namely dates, phone numbers, social security numbers, credit card numbers. These are structured data, while text files, reports, images, video, and so on and so forth are unstructured data. So for those that they do not know about SQL, structured query, the structured query language that was invented by IBM in the 70s, the idea is very simple. This is something that characterizes structured data. These are relational databases, as we say. And in these kind of databases, the data is stored in structured tables. Basically, you have a schema. You say, for example, that I have a user which has a given user ID, and the user is characterized by a name, it's characterized by a zip code, a blog URL, and a blog ID. What is important in SQL is that it allows for combining and joining different kind of tables, right? So you have this format here, but you can also have another database, another table that has to do that has a given ID. These are called primary keys, and you might have here the names, right? And here you might have the URLs and specific characteristics about the URLs. And all of these are connected using, for instance, primary or foreign keys, right? So this is the characteristic of SQL. However, in unstructured data, we do not have any more this kind of systems. We don't have SQL systems or structured database, and we have specific characteristics. These are lots of random reads and writes. Sometimes it is quite write heavy, so we are actually posting a lot of data on Facebook or on social media, which means that this data is basically written on a database on the web. So the writing is extremely heavy in this kind of databases. The foreign keys that they were used a lot in SQL are actually rarely used here, and the joins between tables, between different tables, is basically infrequently done. What we are caring for is speed. What do I mean by speed? By speed, I mean that when you connect on Netflix at home, you want immediately to start the movie from where you left it last time, right? So the information about Netflix, the information that Netflix has about you as a user is stored in these big databases, basically in a version of Cassandra, and this information stores everything. This database stores everything from your inscription to the last minute that you watched a given series, right? A given episode of a given series. So it's schemaless. So we don't imagine that similar types of ideas are used by Netflix to store where actually was your latest where you stopped watching a movie, but the same type of databases are used, not the same database, the same type of databases are used by Facebook to store what was the latest person on Facebook that you liked or that you followed, right? And additionally, because we are talking about really big data, these databases, they have internal systems that they deal with failures. You know that that computers fail, and we will see later on that these big data systems, they consist of millions of machines, all right? And these millions of machines will fail, and because machines fail frequently, the failures that we are going to have will be catastrophic unless we have a protocol to make sure that we have redundancy in the data and that we store data. So this kind of systems, they are very scalable. What do I mean by scalable? Means that they can scale out typically and not scale up. Scale out means that I can use more machines, but not necessarily more powerful machines, right? So what happens is that we will see later on, we have a site where we make everything on, we have a site where we connect computers together, and by keep creating and connecting more computers, we can increase the capacity of our system, all right? And these databases need to take that into account. and names of these databases are key value stores like React, but also key value stores like Cassandra and HBase. Cassandra is the database that is used behind Facebook, and it's also a database that is used behind Netflix. Neo4j is a graph database for graph and data, and MongoDB is typically a database that is used for text storage, large textual data. Have you ever heard any of these systems? Sorry?
What about
Oracle.
Yes.
Well, I'm not aware of the latest characteristics of Oracle databases. From what I recall, these are focusing more on structured data. All right, but I can, if you're interested, you can send me an email and I can search about that. Honestly, I feel that they are mostly focusing, the products that at least I know, they are more structural data, right? And here I give you an example of a relational database management system. A non-relational database management system, no SQL, not only SQL. So in this case, what we have is a key value store. So key value stores hold pairs of a unique key and a value, and they are used to store arbitrarily data indexed using the same key. And one of the most important application programming operations that they are used is get key. So this get key means that get information specific to this key, and also put key value, namely for this, using this key, store this type of value. What is very interesting is that this information might be completely unstructured. So as you can see, for some of these data types, you might be not having specific kinds of either names. Some inputs are missing, actually. And the other thing is that they typically do not support joins, specifically compared to the previous example, the SQL example. We don't have foreign keys in key value stores, right? And there are other types of data. So this is the video that I lost. This was not in my slides. What I was trying to show here is that video is a type of unstructured data. I gave you already the example of the size of video. If I have, for instance, an image, right? I will try to draw this. Can I still draw this here on the board? So let's suppose that I have what I'm trying to explain here, what is a video data type. So video is actually moving pictures, right? So you have many pictures, one next to the other, and this is time here, right? And this is a picture. So basically, each one of them is a pixel, or else alias picture element, all right? So this is a pixel, and this pixel, so you have here the, let's say, M and N. These are the dimensions of the image. And basically, M times N is the resolution, right? The spatial resolution of the image. And I don't know if you have heard about these 10 megapixel cameras, or I don't know where they are right now, 14, 15, or something like that. This means that M times N is equal to 14 million pixels, right? You do the calculations. Now, each one of these pixels basically, typically, is 3 numbers. Each one of them is basically describing a color, the value of a color. Red, green, and blue. All right? The combination of these colors give you the pixel. Now, so how many colors we have in a camera depends on how many bits we use to describe this number here, right? If we have, for example, 8 bits, so if this is something like that, and this is the same thing, this will be a number. So 8 bits correspond to how many different versions of green? Oops. 256 different greens, right? And 256 different, reds, greens, and different blues, right? And all of these, they can create the color that you see in this specific location, okay? Now, at the same time, video is also captured in time with a given frequency, okay? And basically, I think that nowadays cameras, they capture something like 30 frames per second, right? Or 60 frames per second. I think cameras now, I don't know the latest specs, but they're capturing 60, 70, 80, 100 frames per second. So you can imagine the amount of data that is produced. I wanted to give you an example in my slides. Unfortunately, due to incompatibility between the free version of Microsoft Office, it is not feasible to see it. But in my example, I was monitoring with my camera of 10 years ago. I was monitoring a simple scene of a small boat, and that was a 5 minutes video. And a 5 minutes video would cost me 10 gigabytes to store it. Right, 10 gigabytes of data. 10 years ago, there was no flash drive with 10 gigabytes, or at least it was very expensive. And the connections to upload the data, you saw it, we experienced it today. Imagine what would happen if I would try to upload my 10 gigabytes video to the web with the connection that we had today, right? It would take me the entire night to upload it on Facebook. Still, things are happening much faster. So you can store video with much less information. How do we do that? Sorry? Compression. That's a method that we'll see later on, and it's used to extract value. If we hadn't the techniques of compression, forget about watching videos on Netflix, right? Or forget about Blu-ray, YouTube, and all these things, right? And of course, forget about high resolutions and high definition. Oh, okay. So some things are here. Oh, yeah. So I did a small calculation with my ancient camera, which had like 8 megapixel, and was taking for image, and for video was having like 640 times 480 pixels, and with 24 bits and 30 frames per second, a small 5 minutes video of what I was showing you before. It was cost me approximately 9 gigabytes, and for 1 megapixel, 1 megabps connection, it would cost me, without compression, 18 hours to upload it, which is kind of problematic. So last type of diverse types is open versus private data. First of all, you know that EU annual reports on population, employment, birth index, they are available, might be also birth index, but they are available online, and you can get this data, right? Like the OECD data from Belgium. The same thing for published papers. Like in my research group, everything that is public is open data, is free, is available, you can use this data. And here I'm quoting Euler, that open data is the idea that some data should be freely available to everyone to use and to republish as they wish without restrictions from copyright, patents, or other mechanisms of control. There are also public data, which are data released by private companies or individuals or organizations. For instance, the New York Times archive is public data. The Google statistics on search volume is also public data, or other examples is a million songs that they are available on the Amazon Web Service. So public data is data that is released to the public and has some form of restrictions placed on it, right? So if you go, for instance, on Google Images and you click on restrictions, you will see what kind of restrictions you might have on this data, right? So open data is data without restrictions. Public data is data that they might have restrictions accustomed to them. But there are also private data. Private data is data that they are not made available to the generic public. Well, I guess that medical records, financial data, as well as private data on the web, for instance, whatever you put private on the web, is data that you don't want to share, or data that you still want to keep ownership, right? And that's very important. So you need to remember that you are the owner of the data that you are producing. There is rules, strict rules about privacy and about data data ownership in the EU regulations, and also some you know, I think you have heard about the GDPR, right? This is a regulation by the European Union, but there are also similar regulations in the US that forbid individuals or companies to monitor and collect data about individuals without their consent, right? That's a very important right of human, the right of having ownership to the data. And one of the prime elements of data ownership is the right to be forgotten. You know that for every app that you're using, you have the right to ask that app to stop using your data, right? That's called the right to be forgotten. So, unless you have any questions about that, I would like to go into the opportunities that the availability of these different data types can offer. Yes, please.
I have a question related with the real-time versus static data.
Yes.
You were mentioning that, I guess there's an example that the structure that is used to persist or to store real-time data are lists. Is just an example, or is a pattern?
No, it's an example. It's a very simple example. It's a very rudimentary example, as a matter of fact, right? There are different data types that can be used for the kind of graphs. I mean, depending on the complexity, there are different ones, but definitely not that lists are the prime element in that. It's just a simple example. All right? So I'm citing here a report from the McKinsey Global Institute that shows that in 2000, shows the value that has been captured from data so far. Well, the so far refers to 2017. All right? So you can see that in 2017, McKinsey, so first of all, McKinsey made a very popular review and report in 2011 about big data and about their value. And they published that report. It's open. So this report in 2011 was projecting 100 billion revenues for service providers because of location data, and up to $700 billion value to end users because of location-based data, right? According to their estimations, within 5 years, within a period of 5 years, only 50 to 60% of this value has been captured. All right? So, yes, please.
Over which period? They say 700 billion over a 10-year period? Or
Over 5-year period, they did the analysis, yes. So you might ask, why is it so high, right? But imagine the time that we would lose if we wouldn't have Google Maps. I mean, you know, you have now this GPS on the cars, you have even value that is produced because of autonomous driving. And this autonomous driving is based on location-based services, right? And this is a huge business for manufacturers. This could not be captured without location-based data. If we would not know the location of the car and other cars around it, we would not be able to do autonomous driving. We will not be able to navigate in the city, just as we won't be able to do that. I mean, we would, but we'll spend a significant amount of time and so on and so forth, right? But still, location-based services are a good example of a good use of data and a nice development of business. However, there are other examples. In the US retail, for instance, only 30 to 40% of the initially estimated value has been captured in that years. But there are other domains, for instance, manufacturing, where significantly lower, 20%, has been captured, and other domains like the European public sector, where only 10 or 20% is captured. Actually, in 2011, that report was mentioning that by using big data, the European Union could save up to 250 billion euros per year. For instance, they could use data to detect fraud, to improve tax collection, to reduce crime. And unfortunately, out of this value, only 10% of the estimated value, only 10% has been captured. Already, 25 to 50 billion euros are produced in the EU because of data and analytics. However, as you will see later on, the rest of the value has not been captured, and one of the prime reasons is the lack of talent. I will describe later on what do I mean by that. Another important domain where value is not very well captured is in healthcare. You know that I hope you have heard about personalized medicine and personalized health. Only a very small margin of what has been discussed or projected is captured, and this has to do mostly with the sensitivity of the problem. It's very difficult to create data sets because these are very sensitive private data. No one would like to share its own personal data, right? That have to do with health. So it's a very sensitive aspect. But you can see that there is significant value that is only partially captured, right? But still, in the US healthcare, from the 300 billion US dollars that was projected by McKinsey, still at 10% of this has been captured. Approximately 30 billion US dollars have been used, has been captured because of data and analytics. What I would like to have as a prime message today is that data scientists, data analysts, and data and business developers around data will be in a huge shortage in the forthcoming years. All right? And this has been shown by different reports, by different analyses, for instance, by PwC, where they mentioned that while 23% of the educational supply could have data science and analytics skills, and the market is actually demanding much higher than this. 69% of the employers say that they require their job candidates to have data science and analytical skills. All right, so you see the mismatch. 23% they are leaving the university with data and analytics, and 69% are requested by business. Another citation is from the McKinsey. Yes, please.
When you talked about data analytic background, were you referring to which degrees? Like IT or also?
So there are.
Analytic is.
That's a very nice question. So there are different aspects around data. There's not necessarily analytics, because there is data engineering. So databases is part of data. It's a very important skill. Data communications is a very important skill. Processing data is very important. Connectivity is very important, how to make networks. But also business people, that they have expertise in understanding the business market around data is an important skill that refers to data science. Environmental scientists with data analytic skills are in great shortage as well. Business analysts with analytic skills are in great shortage. Statisticians, of course, yes. I refer to this as data analysts, but yes, statisticians are very important. Machine learning people, artificial intelligence, everything that has to do with, understanding, manipulating, creating, and sharing data. And similar numbers are projected for 2024 by the McKinsey Institute. So data can create very disruptive models in different business. I want to highlight some aspects. You know what is orthogonal data? What would that refer to? For instance, business. So here it says that archetype of disruption, data can disrupt domains like insurance, healthcare, and human capital and talent, and how it can do that, how it can be disruptive by using orthogonal data. Can you imagine what does this mean? What is orthogonal to something?
Data that comes from completely different types of it.
Perfect. So imagine, for instance, that you are in insurance, all right, and you try to see how high should be the insurance cost of a person, right? And then you typically go and you ask for a medical record, or you ask for a record of the family, right? Makes sense. But what if you would ask for the social media data? Then you could see, for example, this is you might say, oh, this is completely unrelated. This kind of orthogonal data to what you are looking for, right? Still, by using, for example, social media data, you can see whether this person is skiing. You can see hobbies, you can see other things, and then you can relate to this to understand how critical it would be for this person to have an accident, for example. Other types of disruption is in radical, another example is radical personalization. And this can really disrupt domains like media, right? Imagine a television channel that will produce movies that they are specifically designed for you, or that they knows that you will consume. Something like that is done in Netflix, where it proposes to you, it recommends to you to watch specific movies, or in Spotify that they recommend to you to listen to specific songs, right? This is personalization. But personalization, which is already used in this kind of business models, can be much more disruptive, can depend on context. For instance, using AI, we can predict what is the incentive behind something. When I'm taking my car and I go out in the night, is my incentive to go and get a drink? Then I might have an app on my mobile phone saying, why don't you go this time to this bar, right? So this means extreme personalization, really understanding, using context and using diverse types of data to understand specific aspects about a person. And you can see other examples. The slides will be available to you. And this is a roadmap that has been also developed by McKinsey on how a business can change using data. This is a very important transformation. Typically it starts by trying to understand what are the use cases and the value that can a company extract. Then it has to do by understanding the internal ecosystem, basically what kind of data do you have, how can I put this data into silos, how can I incorporate external data, do I use open data, do I buy privately owned data, how do I merge this data with how do I enhance data. And then the important thing which comes here, for instance, in data science, how do I get insights from this data? How I go from a model of a client-driven organization to a data-driven organization. For example, how do I combine different types of data to create new business opportunities? And then here is where we have the bottleneck of people. We're missing a lot of people here, but also in the next steps where we need to have people that they work with the data and they process and they design the data, but at the same time we need to have management that is able to understand and drive business into the new aspects that have to do with data. So how much time do I still have?
1 hour.
1 hour, that's great. So then in the next part I would like to go in the different methods to extract value, if that would be okay with you. Any questions so far? Yes. Yeah.
Maybe it's part of the scope, but how can you provide health information knowing that health is a private data?
How can I provide health information?
Yes, health information, for example, the amount of people who have specific health or fever, for example. According to your website that you showed at the beginning.
Oh, the health map, you mean?
Yes.
Oh, but this is, you don't say which people have this disease, but you describe the incident. So if someone, if a Salmonella Institute is reported, if someone with Salmonella goes into a hospital and they measure different aspects and they understand, they make the diagnosis that this person has Salmonella, this is a very important information that is stored, and they say Salmonella incident, but they don't say Nikolaos Dilegiannis came with Salmonella, right? and at least they don't make this information public. So the incident of observing Salmonella is important, and then the National Health Organization has this information, and this information is available, but not what kind of, which person has, all right?
So the
This is
priority
private.
here is when the heart is linked to the person.
Exactly, yeah. Make sense? And other questions? No? So let's see how we can extract value. Well, I'm very happy because there are many of these methods that I know on this slide, and they are really used nowadays to extract value out of data, right? So there are different kind of pillars and different kind of use cases. So here we have machine learning, which is a prime way to take data in. It's a set of tools that they take data in and they create insights from the data. And there's also the pillar of data processing, or if you want, more established methods of processing and analyzing data. And finally, there are the use cases that they are developed by the combinations between processing and machine learning. So I will show you specific examples later on about this. So in machine learning, we have different methods, specifically regression. We have clustering, which means how can I group data of the same type together. We also have dimensionality reduction, which basically means how can I go from a large set of dimensions into smaller dimensions and be able to see the data. I also have classification. Classification means that if I observe a certain type of data, how do I classify it in a set of different classes? For instance, an image. Is it an image of a pedestrian? Is it an image of an animal? Is it an image of a car or what? So this is a classification problem. Recently, I don't know if you have heard about these things, but machine learning has been revolutionized by the reinvention of deep neural networks or neural networks. These are mathematical models that they try to imitate how neurons form a deep network that creates cognition in our brain. There is another example, which is reinforcement learning. It's typically used in robotics, and it's used to learn by examples and rewards, right? By actions and rewards. Something that has really, a model that has really, a set of models that has really gained a lot of attention in the recent years is graph deep learning, graph neural networks. And that's because a lot of data, they are connected through graphs, for instance, social networks or 3D models. They are graph type of models. Something quite interesting is dictionary learning. Is basically how I take data and I learn the prime components that construct this data. For instance, see the faces, right? The human faces. There are billions of people on this planet. All of them, they have different characteristics, but all of them, they have a lot of similar elements, right? Grouped together, they have similar elements. So dictionary learning tells us what are the prime, the most important elements that they create a data sample, right? And then deep belief networks, which are versions of, for instance, Bayesian type of networks for deep learning. And then there are aspects and algorithms that they are used to create value out of data. And these algorithms are, most importantly, compression. We said that compression is very important to compact information and to be able to store and manipulate it. but also signal processing. Signal processing refers to a set of techniques, a set of skills that they take data and that they process the data, in the sense that, for instance, they might remove noise. They might complete incomplete data. For instance, there is a set of technologies that they're called image in painting, right? If you take a picture of an image and then you want to remove some part in there, how do you refill this in? This is image in painting, and it has to do with signal processing. Another aspect is something related to what we saw there. You know that video cameras, they are capturing, for instance, 30 or 60 frames per second, right? What kind of television do you have at home? Have you checked their specs? Do you know how many frames per second does your television project? 600 nowadays. So I told you that I have captured 60 frames per second, but I am projecting 600 frames per second, 10 times more, 10 times more. How can I do that?
It's maybe longer.
Sorry?
The first one you did it for
That's
10 times.
for 10 times. Well, you do 10 times the same frame.
Yeah.
I agree with you. That's the simplest method for super resolution in time, right? The simplest method for upsampling, right? But there are other types of methods. For instance, interpolation. You take this frame and this frame, you find the average of it, and or the weighted average of it, and then you have twice as higher the frequency. And there are other techniques that they are in the group of image processing or in the group of signal processing, right? But you just said the simplest one, yeah.
For me, the question is not how, but why? Why do we need 600?
I was about to answer this. Thank you for the question. Any ideas?
To increase the quality
What kind of quality?
of the image,
Sorry?
of the video.
The visual quality, the temporal video quality. So I would propose that so if you have a very dull and very slow movie, which one, let's say, I don't know, Schindler's List, isn't it? It's not a dull, it's a great movie, but it's a very slow movie, isn't it? What other kinds of movie? Anyway, there are movies that they are more slow, but there are movies that they are with a lot of special effects, right? Very fast driving, explosions, etc. If you project this video in a low frame rate, then you will see jumps.
About 600.
Yeah.
60 or 120 is unnoticeable by the naked eye. 600.
Yes, but this is related to the spatial resolution as well, because the resolution of the video is the resolution of the television is very high, the spatial resolution, and your eye will be focusing on specific parts of it. You might be able to see that. That's why they increase also the temporal resolution.
To increase the tightness of the eyes, I guess. So it's not the same.
No, it's the smoothness, the smoothness signal. So you don't get your eye tired because the eye will see what it wants to see, right? So other types of techniques is sorting, right? But also search algorithms, like when you do the page rank and you search with we search the web. Encryption methods to, for instance, encrypt someone's private data, as well as optimization algorithms. I don't know if you heard about convex optimization methods, if you have heard about minimization right, minimization of a function. Also, algorithms that have to do with data communications. How do we send data from one point to the other, either with a wireless link or with a wired link? And control theory. And how can this be used to create value? Well, there are several use cases. First of all, data visualization. An example is the 3D visualization of real-time data that I showed you before. That creates value, for instance, for city planners or for public transportation companies like STIB. Resource allocation, which means which kind of resources in terms of hardware of computing, in terms of memory, should I put for which task or for which kind of data. Predictive analytics. Let's predict, for example, what is the probability of a loan to default. Hyper-personalization, I mentioned it before. Anomaly or trend detection. We are, for example, using video mining algorithms to detect anomalies in video footage from metros, from public places, etc., that they can be used for law enforcement, for example. Forecasting. Forecasting models have been used from finance to weather. Price and product optimization, to understand what kind of products you should recommend and what kind of price you should use, you should propose. And of course, to generate unstructured data. You know, for example, that currently we are able with AI, with artificial neural networks, to generate faces of people that they do not exist. Okay, this is called generative networks. So you can make a Facebook profile with images of people of someone that does not exist. All right. But it's also very interesting to know that with respect to price and product optimization, there are companies that they beforehand predict. Amazon, for instance, it does shipping from the US to Europe, specific products that it knows that they will be consumed. So they're doing a forecasting of the sales in a given area, and they pre-ship. That's why they are so fast. So I'm going to give now some examples of how what do the techniques that I mentioned before mean, okay? Very simple. I'm not going to go into the mathematics of this. I think that in the forthcoming slides, you're going to have the forthcoming lectures, you're going to have lecturers that they will explain some of these things. So I'm only going today to the basic concepts about it, okay? Also, if you see weird things on the slides, that's because of the open office. In the slides that you will receive, this will be resolved, okay? So let's consider the example of auto VLAN, all right? So you are a scientist, a data scientist, a data analyst, and you work for auto VLAN. And you want to be able to predict what should be a good price for a car that you sell, a second-hand car, right? So how can you construct such models? Well, this is a kind of problem that we call a regression. Okay? In regression, the characteristic is that we have access to data. Sorry, let me describe first what do I try to do. So here in this visualization, you see an example data set. We call this a training data set, where we have the mileage of the car in thousands of kilometers. And on the vertical axis, we have the price that this car was sold in the past, right? For this mileage. So we have a car here. This blue point here shows a car. It corresponds to a car. And this is the price that it was sold. And this is the mileage that it had in terms of thousands of kilometers. What you want to do is to find a model that fits in this data. And using this kind of model, you are able to, for instance, you could consider that a straight line that tries to pass from this data. So this straight line here, what you do with this one, you're trying to make this line to be as close as possible, passing from all the possible data points, and to minimize the error between this point here and this point here. Actually, we typically use the squared error, the distance from this point to this point, and this point to this point, the sum of this. So this is a linear model, right? Because this line here is a line. This model is a line. It's a linear model. And if we were able to fit this line, then if we have a new car with a given mileage, then we will be able to predict what will be the best value for this car to sell it, right? So you understand that data science plays an important role here. And that important role, apart from knowing what kind of data for the car, is very important. So because the mileage is not the only important thing an important feature of the car, but it's also the color, the number of doors, when was the car produced, the make of the car, and so on and so forth. But apart from that, a data scientist also needs to be able to create a very accurate model. Because you would say that this model, it is simple and is not capturing very well the data, right? So if you were able, for instance, to create that kind of model, which is a non-linear model, you would see that, for instance, it captures nicer the data, the training data. It fits nicer to the training data because the errors of this line with respect to the existing training data is smaller. And actually, this might give you to a completely different prediction, a much higher value. So it's very important as well to be able to understand how these tools work, because it can really create a lot of difference. You see here a very, very rudimentary and visual example. And this is not real data, okay? So these are examples that I made. What is very important also is that to understand what is a regression problem. So a regression problem falls into the category of supervised learning. In supervised learning, what we have is access to a training data set, and a training data set which has labeled data points. So what is a training data set? The set of these blue circles here correspond to a data set, to a training data set, which we can use to fit a model. But why I call this data set as labeled is because for every of these blue point, I know the mileage of the car, the feature of the car, but I also know the output label, which is the value. Okay, this is the label that I'm trying to predict. Okay, so in labeled data, I have access to the labels that I am actually trying to fit a model that from the features, the characteristics, the mileage, I will be able to predict the label. Make sense? Do you understand it, or should I say it one more time? One more time. So what I'm trying to predict is the mileage, and this is what I call the predicted value, right? And this is the value that I'm using which is called the predictor. All right, the predictor is what predicts the price of the car is the mileage. So I need to create a function that takes as input the predictor, the mileage, and learns to predict the predicted value, the output value, right, the price. In order to create this function, I need to train this function. All right? In order to train this function, I'm taking examples of predictor values and of output values. And I'm learning a model that minimizes the error between what I predict and what is given in my training data. Right? And because I have this access to these labels, I refer to these problems as supervised learning problems, because there is a set of values that are used to help me to supervise my problem. Okay? So this is supervised learning, but it's also very important to mention that it's a regression problem, and a regression problem is that the predicted parameter, the output value, is a continuous value. The price of a car can be from €0 to 20 million, I don't know how much it can be, right? But it can take any value in between. You can buy a car for 14,338.53 euros, right? This is a continuous value, continuous number. Make sense? So if a problem is supervised, so if I have access to labeled data for what I'm trying to predict, and if what I'm trying to predict is a continuous number, then these problems are called supervised learning problems. And specifically regression. So if I have labeled data, these are supervised learning problems, and if I have continuous values that I'm trying to predict, then these problems are a regression. All right? Make sense? Well, an example of yes?
Normally you have several parameters as predictors in order to improve the accuracy of the predicted value.
Absolutely. We have many. Why I wanted to just show one is because for simplicity, of course, and because I could only show two values, right? Because I cannot show you what happens with 4 dimensions or 5 dimensions. If I had an extra set of features, then I would not have any more. If I have an extra set of features, yes, then I would have a 3D curve here, right? And what I would be fitting is not anymore one line, but I would be fitting a hyperspace, right? A hyperplane, right? And then, of course, if I go to the 4 or the 5 dimensions, then my hyperplane has much higher dimensions. And that's why I chose to give you this example to make it visually much more simple. All right? But indeed, in regression, what we are doing, indeed, is we are trying to find a hyperplane that has a minimum error with the predicted value, right? Another example of regression problems is recommender systems. In the past, you know, in Netflix you would get a recommendation based on the number of stars that you would rate a movie. But now you can get, you have recommendation systems that they give you more of a discrete prediction, that they say that this person will like this movie with 95.something%, right? But still, this is a supervised learning problem. regression or classification, we will see it. But what I wanted to say is that this is some kind of a supervised or at least semi-supervised learning problem. So this is an example of a recommender system, and it's modeled using as a problem of matrix completion, right? So you see here movies. I'm trying to explain to you what the recommender system is, a very simple version of it. So here you see movies, right? And here you see users. These are all names of my research group, okay? And here you see ratings that these users have given to specific movies. I think that this is completely at random because I can guarantee to you that I don't really like Crazy Stupid Love. I mean, don't say that to the director of the movies and the actors. They're really nice, but I mean, Interstellar is much, much nicer. So, so you see that some users have rated the movies, the products, the movies in these particular examples, but they have not given a rating for all of them because, for instance, they have not seen it or because they didn't provide the rating. So the problem here is how can we, and here the question marks correspond to not given ratings, right? So the question here is how can we use the available data to fill in the missing entries? How can we try to predict what should be in here, right? What should be in here, what should be in here, what should be in here? You might think that this is an impossible task, right? But do you have a feeling why this is actually possible?
I can use some sort of statistical distribution to kind of have a probability. So for example, we see spectras several times the rating 0 and one time the rating 4. So maybe there's a high probability that the missing rating would be either 0 or 4, and maybe the median would be 2. Anyway, so kind of use.
So you're using statistics based on what I am scoring, right? So you, for instance, in my example, you're using statistics of my score to try to predict this, right? You, for instance, you could give my mean value there, right?
Yeah, I didn't even think about that. But that's sorry.
That's one way. Another idea?
I think he was focusing on the same movie.
All right. Yeah. Okay. It's the same thing. Yes.
I would do both.
Sorry?
I would do both. So using the individual and then maybe categorize the movies that we have, taking some characteristics. So Yes, I Love You goes in a similar category with Crazy Stupid Love, and then based on the ratings, you predict the value.
It is very actually similar to what you described with what existing methods work on. Please, yeah.
My question is, why should we predict the value?
Well, if you predict that value and you predict a 5 here, you might wish to say to Nikos, you should watch Interstellar. And then if you have a system that basically, if I am using Netflix and it proposes to me nice movies and I really enjoy it, then I will keep using my inscription, right? If I pay to Spotify for 1 month to use it and it recommends me very nice songs when I'm going to my office, then I really enjoy that and I really continue my inscription, right? It's the same algorithms that they're used to propose to you friends on Facebook. And the moment that they propose you more and more friends, you get more and more involved into Facebook. And you get more time there, and then that's great.
I would take a completely different approach.
Yes?
Duke and Tim,
Yes?
the two films that they have rated, they put the same score. For
Yeah.
Yes, I Love You, they put 0, and for Interstellar, they put 5.
Yeah.
So that could mean that they have a similar taste,
Yes?
and then we could infer that for the other 3 movies which are missing on one of the sites, they would rate the same as the other person.
Exactly. Yes. So first of all, both approaches, which you describe with words, is basically the main two approaches that they are used in the state-of-the-art recommender systems. And in fact, the combinations of the two give you the best results. In the one sense, on the one hand, we have what we call entry based or like nearest neighbors. So what is my nearest neighbor? What is my closest movie? Let's use this one. But on the other hand, we also have model-based approaches where we say that, well, there will be some groups of users and that they are voting similarly, exactly as you mentioned. And there are some groups of movies that they are very similar, so they will get similar scores, which means that this matrix has a given form, follows a given model. It's not the columns or the rows of this matrix are not independent to each other, they are highly dependent, which means that this, if you recall from mathematics, which means that this matrix is a low rank matrix, has lower dimensions than the dimensions that they are here, right? Now you will probably ask me, you know what, how much incomplete are these data sets, right? So
They get better over time.
first of all, they get better over time, that's very important.
After a while, you can just fill in Nikos, you would rate the Stella.
Yes, but I agree with you, but unfortunately, the problem is a little bit also very complicated because Nikos' taste changes over time as well. The moment you start learning him, you will lose him. I mean, you might start voting with a different. Yeah. So this is a very recommendations. It's a very hot problem nowadays, and it's an active field of research. And of course, there are systems that they do dynamic prediction of recommendations and context adaptive, and this is a very interesting problem. Yes.
The problem is actually that Nikos never gets the chance to watch Spectre again. Right? Will never be recommended to him.
Well, I watched it already, and I said I don't like it.
No, the five.
Oh no, it's
zero, right?
It's a zero, yeah.
The zero will never be recommended.
If I am voting, yes, if I am voting in honestly, and if the system is good, it should not recommend me again James Bond movies, right? Or at least not James Bond movies with Daniel Craig. But another thing that I wanted to say is that these data sets are highly incomplete. So you can play with such a data set. The Netflix has released a data set some years ago. I think it was 2010, 11. So this data set consists of, if I recall correctly, well, some thousands of users and some hundreds of thousands of products, of movies, or vice versa, thousands of movies, and which is really, we're talking about tens of millions of entries, and out of them only approximately 1% is filled in. And it was a big price. They released the data set and they put a price, $1 million US dollars, for the best winning algorithm for that. It's called the Netflix problem and the Netflix prize. So there is a team that got the award, that they made the best algorithm. But what is also very interesting is that there have been people that they used this data set, and they also used comments on IMDb, and they managed to understand what was the user. They manage to get the name of the user from the dataset and how a specific user would rate. So, I mean, the dataset of Netflix is not, it does not contain the name of users. It only contains user identifier, 1,500, etc. But because the people cross-correlated content in IMDb from people that they were really writing their name and they were saying which movies they liked, and this was freely available, they cross-correlate with this dataset and they try, and they, with a given accuracy, they manage to find the users. So that's an example of how careful we have to be with what we disclose on the web. So this is another type of supervised learning. This is called classification. So imagine a problem of, there is actually this kind of problem, for the disease, for sepsis mortality, okay? So what is the probability of a person to die because of sepsis? In order to get this probability, what they do is that they do a test, and it's called Apache 2 score at the baseline. The medical terms, I don't really know them. And based on the value of this test, they can predict what is the probability for the problem of sepsis for a specific person to be to basically lead to death, right? So you collect, how do they do that? They have already collected at hospitals a big amount of data from scores of this test, and also they have observed cases, all right? With red crosses or X's, you see people that they have disease, and with blue circles, you see people that they actually survived. So you see that this creates a threshold. You see that there are some extreme cases above values of 25 Apache score in the baseline that they survived. But typically, if you have something like that, if you have a score which is lower than a given threshold, then you have high probability to live. Of course, the lower your score, the higher your probability, and vice versa. And this kind of models, this kind of techniques, they refer to classification, and of course supervised learning. So, yes?
What is the XX?
It's the value of the score. This score is some kind of test. It's called Apache 2 test, and they check the score of this test in the baseline. It's probably kind of blood test, and then I don't really know. Okay, and then they test they check the value of that. So this is called it is again a supervised learning problem, because you have access to a training data set which contains predictors, namely values of the Apache 2 score, and also you have access to labels, which are whether people are died or not, that they have the specific value in the score, right, in the test. So you have labeled data, but what changes with respect to the previous problem is that our data in this case are discrete. Our labels are discrete. So the predicted parameter, the parameter that we try to predict, in this case whether we will die or we will survive, is a discrete parameter. Takes only two values in the specific case. Okay? So do you see the difference between regression and classification? They are both supervised learning problems. For both cases we have labeled training data, but the difference is that in classification the data set is, the predicted value is discrete. And then I'm going to a third category of problems, which are called clustering problems. In clustering, what we try to do is to group similar data together. Therefore, we need to have a criterion for this similarity, and we need to have a kind of an algorithm that learns how to group this kind of data. So for this particular problem, I call this the Pizza Hut problem, because for instance, I'm going to tell you an example version of clustering, an example problem of clustering, right? Here you see the city of, part of the city of Brussels, and you see here with these white dots, these are addresses of people that they have ordered a pizza from, well, you know, from a pizza store, right? And then what your boss wants to know, or what the owner of this pizza place wants to know, is which are the locations that he would like to open 5 stores, 5 new stores, that they would do only delivery. And these 5 stores would be in strategic locations that they would really minimize the distance that a delivery person would have to spend, so that it can basically deliver all the orders that we'll receive from clients, right? So basically what you want to do is to say that I'm going to group orders that they are in similar locations together. So these are data points, therefore, which you want to group them together, and you also want to find the center of gravity, the center of locations, to serve these points, right? So in this particular problem, the data have features, and these basically are the, if you want, the locations, the longitude and latitude. These are 2-dimensional fixture vectors. You might also have, like, how many times did I order? This can also be a feature, right? But let's keep this aside for the moment. And what you try to do is to try to group together similar points. So what are the similar points here? So in this case, because our features are the locations, and because our distance could be, for instance, the Manhattan distance or the distance in kilometers on the street network, then I will try to group together points that are close in terms of the longitude and latitude. So these are, this is what unsupervised learning is doing. Unsupervised learning has access to data that they are not labeled. We are not given any training set that will tell us these all together should be grouped, right? We are just given the data. We are not given labels. We don't know for this data, for instance, which should be grouped together. We try to learn this. So because we don't have any labeled data, any labeled training data, then this problem is called unsupervised learning, right? And the clustering problem in unsupervised learning is basically a type of problem that tries to group data together, all right? And this could be, for instance, a nice example of how k-means would work. And you can see, for instance, that if you would run k-means, you would group together these points into, and you would also get the center of gravity.
But the machine is, because I did it visually and I come out to about the same places.
Yeah, I also did it. This is not an algorithm running. This is a made-up visualization to explain you the problem. It's not that the algorithm did that.
But the algorithm should be then.
The algorithm, this problem can be really easily solved with k-means, and it will give you that. Yes. The machine will group them like this, for sure. Okay. But there is also another type of dimensionality reduction problems, and this, there's another type of unsupervised learning which has to do with dimensionality reduction. Okay? And an application of this is visualization. What do I mean by dimensionality reduction? You mentioned before that you know, a car does not only have the mileage, but it has many other parameters. How many parameters can it have? Like many, right? And what if you want to visualize, to see in a plot cars that they are a little bit anomalous, that they don't look like cars of other similar cars? How can you visualize all these features if you have, like, you collect from every car something like 100 features? How can you plot cars? It's impossible to do that with 100 dimensions. We don't have any way to visualize 100 dimensions, right? It's actually very difficult for us to even conceive 100 dimensions. So there are techniques that what they're doing is that they're trying to take data from high dimensions and trying to find the lower important dimensions, okay? For instance, you were mentioning before that the data, if they are in a three-dimensional space, the data can live into something like a hyperplane, right? So if we know that the data live in a perfect hyperplane, a linear hyperplane, then we don't need an extra dimension. We can just go with 2 dimensions, and so only the direction of how the data is increasing, right? This is what I mean by dimensionality reduction. So in dimensionality reduction, you go from high dimensions to significantly lower dimensions. This is another example of unsupervised learning. We don't have labeled data, again, and because we are trying to find the latent dimensions, the hidden dimensions in our problem, that's why we are calling this problem a dimensionality reduction problem. An example of visualization is, for instance, how you can visualize the frequency of tweets in Brussels, right? So you know that what you can do there, for instance, is that you have users that they are tweeting about different aspects, okay? About different products, for example, about different events, and they are moving in the city of Brussels. The question is, can I visualize how these users are moving, how many tweets are sent from each location, and what are the topics discussed? You can use, for instance, techniques like visualization. So you can calculate the histogram for every location, how many tweets are sent. You can use color to encode the topic, the sentiment. Is this user positive against this event or negatively positioning himself? So all these things, they create a set of tools, visualization tools, for which dimensionality reduction is a prime component. And the most important technique of dimensionality reduction is called principal component analysis, okay, PCA. Of course, you can also use other types of methods to visualize information, for instance, using graphs. This is a result from a study that we did at the university, where we were trying to identify the most important players, the most important communities of practice in social media in the city of Brussels, all right? So it's a study. We used the API of Twitter between June 2016 and January 2017, and we monitored 4 big Twitter accounts that they were discussing about communities. They are creating communities in Brussels. Café Bruxelles, for instance, is one of them. The VRT Sandbox. I don't recall the others. So these are big media, communities in Brussels about specific topics. And we basically crawled on the Twitter API, the mentions of these communities of practice. And then what we did is that we created a graph, right? What is a graph is that you have a node here, and this node is a person, right? Represents a user. And this user here is connected with his user because, for example, he has or she has liked one of her tweets. And how many connections this user has is also making this user, this circle bigger and bigger. For instance, this node here has a lot of connections with other nodes, so it's a significant node, and this increases its size in terms of the circle, right? And at the same time, the color here is encoding the different accounts, and so on and so forth. And by creating this kind of visualization across time, you can see, for example, that indeed Café Bruxelles is the most influential community of practice according to social media, according to that period in Brussels. All right? That was a scientific study that we helped communication scientists using data analytics to identify the most important communities of practice. The paper is available online for those that they are interested in communication sciences. You can see. So typically, to give you an example, communication scientists, to be able to understand this, they need to create questionnaires, right? They write questions like, which community of practice do you follow? Where do you go? And they give these questionnaires to people. And then people, they fill this in, and then they give it back, and they make a study out of this. So in that particular paper, we compared such a study, which took some amount of time, and it was based only on 100 questionnaires. And we compared what you can do and what you can learn with big data. And the result was really astonishing. Okay? So you can see that using data and using analytics, you can really understand and capture more adaptively what happens in the city. So how much time do I have?
20 minutes.
All right. So I hope you're not still tired. A little bit? Okay, but we're going to see some exciting stuff for the next minute, so I think it's going to be easy and simple. So example of extracting value is, can we use social media to understand, for example, where users reside and to try to crawl what is available openly to recommend them products. So to do that, you need to know where is the location of this kind of users. And we have developed such a tool that it basically takes into account information, diverse type of information, like what kind of people do you follow, what do you say on social media, what time do you post information, and then based on this, we're able to create a model, a mathematical model that would predict, based on this information, a rough location of yours, right? And then based on that, people could really recommend products. They really recommend you what kind of transportation you should use, and so on and so forth. So obviously, imaging is a very important aspect of unstructured data, and currently using satellite imaging, for example, we are able to do a lot of things. You know that across the world we are actually monitored 24/7 by satellites that they capture information about the geographical aspects of the Earth and how things are changing on the surface, but they're also capturing information about meteorology, information about climate, information about the pollution, the atmospheric pollution. And by using artificial intelligence and image processing, we are able to analyze this data and to extract value. An example is semantic segmentation. We have pre-trained models that take an input of a satellite image and they immediately produce labels for every location. So we know, for instance, that this pixel here, this area here, is a tree area, and that this is a house, and that this is a street. Okay? So you take the image from the satellite, you put it through a model, and the model learns to semantically segment the image, tell you which part of the image corresponds to which type of information. That's very important. Can you imagine application scenarios where this can be used? Yes, please.
I met guys that use this kind of things to detect where people have their pools, so water, so that people can tax on those pools. And also, I don't know what the other uses.
What kind of people do you know?
No, I met them into
An
an event.
event?
I met them,
Via. Correct. Other kinds of information? That's a nice example, by the way. Other kinds of applications that you could imagine? Sorry?
Face recognition.
Yes, but let's stick for the moment for this particular example of semantic segmentations of satellite imaging. Where could you use this kind of thing? If you, yes, please.
Try to find some spots where we can build some buildings because they are in a space.
For city planning, let's say, right? Yes. Another thing, of course, is what happens if there is a natural disaster. You know that there are satellites like Copernicus. It's a system from the European Union that monitors the area of Europe, and if there is a natural disaster, you can see, you can compare the before with the after, and in that way you are able to act upon a disaster, to send troops, to send you know, to send the police, the fire brigades, and so on and so forth, right? And of course, to understand the vegetation, to understand rivers, water management, pollution management, and so on and so forth. This is very important information about the Earth. And this is basically what I was talking to you before. This is an example of using cross-modal retrieval. So what is this problem here? We try, this is a demo available on the web. We try to cross-correlate text with images, not through metadata, but just let's train a model that takes as input a text that corresponds to an image and an image and tries to couple the two, such that you as a user, if you write text to describe an image, you can search and you can find images that describe, that basically visualize what you described. And this is not through metadata, right? Because a lot of information is captured nowadays, and it does not contain any metadata. Whatever images you post on social media, it doesn't necessarily, you don't post these images with metadata, right? So this is, and of course you can do the opposite. If you have such a coupling system, you could put an image and then immediately you can retrieve the text that this image corresponds to. Although I still agree with you that the killer application is the opposite. Yes?
But for the training, you need to have the caption of each image.
Yes.
So can we consider it as the metadata of the photo?
Yes.
For the training of the model?
So in the training, you could use the metadata, for example, to do that, but not in the actual testing. In the testing, you are assuming, and you, of course, do not have access to metadata.
To train the model, you need...
To train the model, yes, you need. But for the application of the model, you do not need, because you actually are supposed not to use them. No, actually, you don't have this kind of thing. Start from current slide. Okay. So another type of techniques that they are used nowadays is what we call as phrase localization. Actually, this technology of trying to couple text with imaging, it becomes more and more concrete nowadays. You can really use methods that they can localize a phrase in an image. You write a phrase and it will find the box that basically this is contained in the image. You write, for instance, clothing, a black shirt, and you basically have this, right? So if you create this kind of models, you type a sentence that describes an object that you see in the image, and then the algorithm will just go and localize it. But at the same time, if you give an image, the algorithm, the other way around, can find all the different phrases that they are contained in this image, right? This is called phrase localization, and it can be used for storytelling. If you have very nice methods like that, you can post a video, you can put a video on this tool, and it will make a text out of your video. It will describe with words your video. Isn't it amazing? At the same time, you can interact with text. So I mentioned before as well generative networks that they use to generate images of high resolution of people, for example, or landscapes. So you learn to generate patterns, realistic patterns that they can look actual and real, but they're actually fake. And this relates to, I don't know if you have heard about this. Have you heard about deep fake? That they can manipulate content using deep models to, for example, place the face of a famous actor in a video that you recorded of yourself, or place your face in a famous movie. And that basically is not like a Photoshop trick where you can really see it, but it's you won't be able to understand the difference. So artificial intelligence and computer vision have evolved in ways that you are actually currently cannot see the difference between fake data and actual data. And here we have to be careful, and there is a lot of discussion around that. And there's also a lot of discussion about ethics in artificial intelligence. And now with the generation of the new types of technology like autonomous driving, ethics in artificial intelligence and in data will be a very important aspect. How do you train an algorithm to recognize whether or to take a decision that is very important about the default of a loan? How can you train an algorithm that take a decision whether it will, in an event of a crash, it will choose the car, for instance, to go outside of the street and maybe potentially kill the driver, or hit another car and potentially kill another human person. So these are ethical questions that they start to arise from the interaction between artificial intelligence and systems and machines. And this is a very active also field of research, and it's a very interesting part. And at the same way that you are generating images, you can also generate images from text. You can write text that describes an image, and then the artificial intelligence algorithm will be trained to take as input this text and to produce an image, an artificial image that is basically describing your text, right? And this is very interesting because you know that we have been told that books, this is imagination. This is imagining, because when we read books, we read text, and then based on the images that we have in our minds, we produce a story. We produce a video in our mind, a film in our minds, right, when we read a book. These tools, they make it. You take text and it produces an image. This is, for example, you can see I also added in the text the paper that you can go and see how they do it and what they exactly do it. And the same way, they can really change the content in the images. They can change different aspects of this. For instance, they can turn zebras into horses and horses into zebras. They can go from a winter image to a sunny summer image, and so on and so forth. All right. So content nowadays is being manipulated in the ways that you cannot imagine with generative networks. So if I manage to, if I try to categorize what I just said before with respect to learning, there are different aspects of learning, and I focused here on supervised and on unsupervised learning. In supervised learning, we try to learn a model based on labeled training data, and if what we try to predict is continuous, then we fall into the category of regression. If what we try to predict is discrete, then we are addressing the problem of classification, and there are different ways to do that. That will be in forthcoming lectures. Then you have another type of learning, which is unsupervised learning. In this case, you have no labeled data. And you have two different types of problems, specifically clustering, where you try to learn to group data together, and also dimensionality reduction, where you try to learn latent dimensions of your data. And closing, how many minutes we still have? 5 minutes. I would like to pose some questions to you to evaluate you, because you know I have to give a score after today. So I really need your, I'm not going to put any score, it's just, but it's just to close it, I wanted to to ask you a small set of questions. So what kind of learning problem do you think that the Google News is solving? So, you know, Google News is you type, you basically type some words, or you have seen some movie, some news before, and then this is basically projecting some news. So what kind of learning?
The freshest news
Yeah.
around the globe.
What kind of, is it supervised, unsupervised?
Completely unsupervised.
It's unsupervised learning. And what kind? Is it clustering? Is it dimensionality reduction?
I use it often.
Maybe clustering because it would give you the news from your area maybe more often than any other area of the world.
It will be clustering because it will try to find, indeed it's clustering because it's trying to find similar news to show, right? And of course, there are no labeled data. What about optical character recognition? You know that there are trained models that you take a picture, right? And then I don't know if you have used this app that takes a picture of a business card and then immediately places all the information on your mobile phone. What kind of problem do you think is this? Is this supervised or an unsupervised learning problem? I mean, the problem of taking.
At the start it was supervised.
Sorry?
At the start
It is indeed a supervised learning problem. And now, is it a regression or a classification problem?
regression.
Other ideas? Well, classification. But why it is classification? Because for every of these, so every of these pixel here, or every of these, let's say, group of pixels here, they will be given a label, right? And these labels are discrete because you have 24 letters in the Latin alphabet, right? You don't have, sorry? 26, sorry, yes. 24 letters in the Greek alphabet, right? 26 letters in the Latin alphabet, right? So it's a discrete set of labels. What about this? So this is a table that contains state information. This is the different states in the US, and here you have the number of malls, and based on the number of malls you have the sales in millions of dollars, and you want to predict what will be the sales in another state if you have the number of malls that they are available in this state. Yes, a regression problem. It is a supervised learning because you have access to this. Yes?
You have the amount of modes.
Yes?
Where?
Well, if I had another one here.
Oklahoma.
Yeah, say Oklahoma, yeah. What about Oklahoma? If I had the number of malls and I want to predict the total number of
So you need to have the amount of modes.
Yes, I have it.
It's not there.
Okay.
I was trying to calculate it.
I have it written here. And, well, the final one is a simple one. You know that every mail software that respects itself, it has some kind of a spam detector in there that tries to, based on frequency of specific words or other types of models, try to predict whether an email is a spam or not, right? And this is, of course, a supervised or an unsupervised learning problem. What do you think?
We can report spams as humans, so maybe it's supervised.
It is supervised, yes. And regression or classification? It's classification because we have only two classes, spam or not, right? So it's a discrete set of classes, and that refers to classification. So that will be it for today. I would like to thank you for your participation and for your time. I hope you enjoyed this lecture as much as I did. And well, sorry for the delay in the beginning due to the technical issues. Next time it will be resolved. All right? Thanks a lot.